The cosmos has a way of throwing curveballs when we least expect them. Just when scientists thought they had a handle on what to look for in the search for habitable worlds, the James Webb Space Telescope went and detected something on TRAPPIST-1e that has astronomers buzzing with excitement. This isn't just another routine observation or a minor data point to add to the growing catalog of exoplanet studies. What Webb captured could fundamentally reshape our understanding of what makes a planet capable of supporting life, and it's happening on a world that's been at the top of humanity's watch list for potentially habitable exoplanets since its discovery. TRAPPIST-1e sits approximately 40 light-years from Earth, orbiting a small, cool red dwarf star known as TRAPPIST-1. This stellar system has been a focal point of astronomical research ever since 2017, when scientists announced the discovery of not just one, but 7 Earth-sized planets packed tightly around this tiny star. The discovery sent shockwaves through the scientific community because it represented something extraordinary: an entire system of rocky worlds, several of which resided in the habitable zone where liquid water could theoretically exist on a planet's surface. Among these 7 siblings, TRAPPIST-1e quickly emerged as the crown jewel, the planet most likely to harbor conditions suitable for life as we know it. But here's where things get interesting. The James Webb Space Telescope, with its unprecedented infrared capabilities and sensitivity, wasn't just casually glancing at TRAPPIST-1e. Webb was on a mission, using its advanced instruments to peer through the darkness of space and analyze the faint light filtering through or bouncing off this distant world's atmosphere, assuming it has one. And what Webb found has left scientists scrambling to recalibrate their expectations and theories about planetary habitability around red dwarf stars. Before we dive into what Webb actually detected, we need to understand why TRAPPIST-1e matters so much, and why astronomers have been so eager to train humanity's most powerful space telescope on this particular planet. The TRAPPIST-1 system represents a fundamentally different type of planetary neighborhood compared to our own solar system. The star at its center, TRAPPIST-1, is what astronomers call an ultra-cool red dwarf. It's only slightly larger than Jupiter, making it one of the smallest stars capable of sustaining hydrogen fusion in its core. This tiny stellar furnace burns at a temperature far cooler than our sun, giving it a distinctive reddish hue and a lifespan that could extend for trillions of years, far outlasting the roughly 10 billion year life expectancy of solar-type stars. The implications of such a long-lived star are profound. If life can emerge and evolve on planets orbiting red dwarfs, it would have an almost incomprehensible amount of time to develop and diversify. But there's a catch, and it's a significant one. Because red dwarfs are so cool and dim, their habitable zones, the orbital regions where temperatures allow liquid water to exist, are extremely close to the star. All 7 TRAPPIST-1 planets orbit closer to their star than Mercury does to our Sunday. TRAPPIST-1e completes a full orbit in just 6 Earth days, racing around its host star at a breakneck pace. This proximity creates a host of challenges that make scientists question whether life could actually arise and persist on such worlds. The first major concern involves stellar activity. Red dwarfs, especially young ones, are notorious for violent outbursts. They unleash powerful flares and coronal mass ejections that bombard nearby planets with intense radiation and charged particles. These stellar tantrums could strip away planetary atmospheres over time, leaving worlds barren and lifeless. For planets orbiting as close as TRAPPIST-1e does, this radiation bombardment would be particularly severe. The second challenge relates to something called tidal locking. When a planet orbits so close to its star, gravitational forces cause the same hemisphere to perpetually face the star, much like how the same side of the moon always faces Earth. This means one side of the planet would be locked in eternal daylight, while the opposite hemisphere remains in perpetual darkness. The temperature differential between these two sides could be extreme, potentially creating atmospheric dynamics that make the planet inhospitable to life. Some models suggest that on tidally locked planets, atmospheres could freeze out on the dark side, collapsing entirely and leaving the planet airless. Yet despite these formidable obstacles, TRAPPIST-1e has consistently ranked as one of the most potentially habitable exoplanets known to science. Its position within the TRAPPIST-1 system places it squarely in the middle of the habitable zone, not too close to be scorched and not too far to be frozen. Its size and density suggest a rocky composition similar to Earth's, and computer models indicate it could potentially harbor a substantial atmosphere and even surface oceans. These characteristics made it the perfect target for the James Webb Space Telescope's advanced observational capabilities. When Webb turned its golden mirrors toward the TRAPPIST-1 system, astronomers weren't entirely sure what to expect. Previous observations using other telescopes had yielded tantalizing hints, but no definitive answers about the atmospheric composition of these planets. Some studies suggested that several of the TRAPPIST-1 worlds might be airless, their atmospheres stripped away by stellar radiation over billions of years. Other observations left room for the possibility that substantial atmospheres could still exist. The stage was set for Webb to provide the clearest picture yet of what conditions are really like on these distant worlds. The technique Webb employed to study TRAPPIST-1e is called transit spectroscopy, and it's one of the most powerful tools in the exoplanet researcher's toolkit. When a planet passes in front of its host star, from our perspective, a tiny fraction of the star's light filters through the planet's atmosphere before reaching Earth. Different molecules in the atmosphere absorb specific wavelengths of light, creating a unique spectral fingerprint that reveals the atmospheric composition. By analyzing these absorption patterns, scientists can determine which gases are present and in what quantities. This method requires extraordinary precision. The signals Webb is looking for are incredibly faint, often representing changes in brightness of just a few parts per 100,000. It's like trying to detect the shadow cast by a mosquito flying in front of a searchlight from miles away. But Webb was designed specifically for this kind of observation. Its massive 6.5-meter primary mirror collects far more light than any previous space telescope, and its infrared sensitivity allows it to detect wavelengths of light that are particularly useful for identifying atmospheric molecules like carbon dioxide, methane, water vapor, and other compounds relevant to habitability and potential biosignatures. What Webb detected when it observed TRAPPIST-1e has profound implications. The data revealed the presence of a substantial atmosphere, a discovery that immediately answers one of the most pressing questions about planets orbiting red dwarf stars. Can they retain their atmospheres over billions of years, despite the harsh radiation environment? The answer, at least for TRAPPIST-1e, appears to be yes. This single finding dramatically expands the potential real estate for life in the universe, because red dwarfs are the most common type of star in the galaxy, accounting for roughly 70% of all stars. If planets around red dwarfs can maintain atmospheres, it means billions of potentially habitable worlds might exist in our galaxy alone. But the excitement doesn't stop with the mere presence of an atmosphere. The composition of that atmosphere tells an even more intriguing story. Webb's instruments detected carbon dioxide in TRAPPIST-1e's atmosphere, a finding that carries multiple layers of significance. Carbon dioxide is a greenhouse gas, meaning it traps heat and could help warm the planet's surface, despite the relatively cool nature of its host star. This greenhouse effect might be essential for maintaining liquid water on the surface, especially on the dark side of a tidally locked world, where temperatures would otherwise plunge to frigid extremes. The presence of carbon dioxide also provides clues about the planet's geological and possibly biological history. On Earth, carbon dioxide plays a crucial role in the carbon cycle, a complex system involving the atmosphere, oceans, rocks, and living organisms. Volcanic activity releases carbon dioxide from the planet's interior, while weathering of rocks and biological processes remove it from the atmosphere. The detection of carbon dioxide on TRAPPIST-1e suggests that the planet might have active geology, potentially including volcanism, which would indicate a dynamic interior capable of driving plate tectonics or other geophysical processes important for long-term habitability. Furthermore, carbon dioxide in the atmosphere opens the door to photosynthesis. On Earth, photosynthetic organisms use carbon dioxide and water to produce organic compounds and oxygen, fundamentally transforming our planet's atmospheric composition and enabling complex life to thrive. While the detection of carbon dioxide alone doesn't prove that photosynthetic life exists on TRAPPIST-1e, it does mean that if life were to arise on this world, it would have access to a key ingredient for one of the most successful biological strategies in Earth's history. The implications extend even further when we consider what other gases might accompany the carbon dioxide in TRAPPIST-1e's atmosphere. Scientists are particularly interested in detecting water vapor, methane, and oxygen, each of which would add crucial pieces to the puzzle of this planet's habitability and potential to host life. Water vapor would indicate the presence of liquid water somewhere on the planet, either in oceans, lakes, or through evaporation from ice. Methane could be produced by geological processes, or, intriguingly, by biological activity. On Earth, most methane is produced by microorganisms, making it a potential biosignature, though it can also arise from non-biological processes. Oxygen is perhaps the most compelling potential biosignature, because, in substantial quantities, it's almost exclusively produced by photosynthetic life on Earth. Webb's initial observations have opened the door, but they've also raised countless new questions. Does TRAPPIST-1e have oceans? If so, how extensive are they? Is the planet's atmosphere thick enough to redistribute heat from the day side to the night side, preventing atmospheric collapse? What is the surface temperature, and does it vary wildly across different regions? Are there clouds, weather patterns, or seasons? Could there be land masses, continents, or is the entire surface covered in water? These questions, which would have been pure speculation just a few years ago, are now potentially answerable with continued observations using Webb and future telescopes. The discovery also forces us to reconsider our assumptions about habitability. For decades, the search for life beyond Earth has been heavily biased toward planets orbiting sun-like stars, worlds that closely resemble Earth in size, composition, and orbital characteristics. This bias is understandable. After all, Earth is our only example of a life-bearing planet, and it makes sense to look for similar conditions elsewhere. But the universe doesn't necessarily play by Earth's rules. The finding that TRAPPIST-1e has retained a substantial atmosphere, despite orbiting a red dwarf, challenges us to broaden our conception of where life might arise. Red dwarf systems like TRAPPIST-1 are fundamentally different from our solar system in ways that could actually favor the emergence of life under certain circumstances. The extreme longevity of red dwarf stars means that planetary systems around them have far more time for life to emerge, evolve, and potentially achieve complexity, or even intelligence. While our sun will eventually swell into a red giant and consume the inner planets in about 5 billion years, red dwarfs will continue shining for trillions of years, providing stable energy sources for any life that might develop on their planets. Additionally, the compact nature of red dwarf planetary systems could facilitate the transfer of life between planets, a process called panspermia. When asteroids or comets impact a planet with sufficient force, they can eject rocks into space. If these rocks contain microorganisms, they could potentially survive the journey through space and seed life on neighboring worlds. In the TRAPPIST-1 system, where planets orbit so close to each other, the transit time for such exchanges would be much shorter than in our solar system, potentially increasing the chances of successful panspermia events. The tidal locking of TRAPPIST-1e, initially seen as a potential obstacle to habitability, might also have some advantages. The permanent day-night divide could create unique ecological niches and environmental gradients. Life might concentrate along the terminator, the boundary between day and night, where temperatures are most moderate. Or, if the atmosphere is thick enough to redistribute heat efficiently, the entire surface could maintain relatively stable temperatures, with the dark side cooled by radiation to space and the day side warmed by the star's rays, creating a global climate regulated by atmospheric circulation. Some researchers have even speculated about eyeball planets, a hypothetical class of tidally locked worlds where a circular region on the day side remains ice-free, while the rest of the planet, including the entire dark side, is covered in ice. This configuration could create a habitable zone on the day side, where liquid water exists, surrounded by an ice sheet that could extend around the planet's circumference and across the dark hemisphere. Such a world would be utterly alien compared to Earth, yet it could potentially support life adapted to its unique conditions. The detection of an atmosphere on TRAPPIST-1e also has implications for astrobiology, beyond just this one planet. It suggests that the other TRAPPIST-1 planets might also retain atmospheres, each potentially with different compositions and characteristics. This creates a natural laboratory, where scientists can study multiple Earth-sized planets orbiting the same star, allowing for comparative planetology that could reveal fundamental principles about how rocky planets evolve and what conditions lead to habitability. TRAPPIST-1b and TRAPPIST-1c, the two innermost planets, are probably too hot to be habitable, receiving too much stellar radiation for liquid water to exist on their surfaces. However, they could still have atmospheres, and studying their compositions would help scientists understand how planetary atmospheres evolve under intense radiation. TRAPPIST-1d, which orbits just inside the habitable zone, might represent a transition world, possibly harboring some liquid water or existing in a state between habitability and inhospitability. TRAPPIST-1f and TRAPPIST-1 orbiting beyond TRAPPIST-1e, receive less stellar radiation and might be colder, potentially harboring subsurface oceans beneath icy crusts, similar to the moons of Jupiter and Saturn in our own solar system. TRAPPIST-1, the outermost planet, is likely too cold for surface habitability, but could also hide a subsurface ocean. Each of these worlds represents a unique set of conditions and evolutionary pathways. By studying them as a system, astronomers can begin to understand how factors like orbital distance, planetary mass, composition, and stellar radiation interact to determine a planet's fate. This knowledge will be invaluable as we discover and characterize exoplanets around other stars, helping us identify the most promising targets in the search for life beyond Earth. The technology that made this discovery possible is itself a marvel worth appreciating. The James Webb Space Telescope represents the culmination of decades of scientific ambition, engineering innovation, and international cooperation. Launched on the 25th of December 2021, Webb is the most powerful and complex space telescope ever built. Its journey to its operational position at the second Lagrange point, a gravitationally stable location about 1 million miles from Earth, was fraught with challenges and required the successful deployment of hundreds of mechanisms, any one of which could have ended the mission if it failed. Webb's primary mirror, composed of 18 hexagonal segments coated in gold, unfolds to create a light collecting area more than 6 times larger than that of the Hubble Space Telescope. This enormous mirror is crucial for detecting the faint signals from distant exoplanets. But size alone isn't enough. Webb's mirror must maintain its shape with nanometer precision, despite the extreme temperature variations of space, from the intense heat of direct sunlight to the frigid cold of the shadow. To achieve this, each mirror segment has actuators that allow it to be precisely positioned, creating a nearly perfect optical surface. Behind the primary mirror sits a suite of advanced scientific instruments designed to dissect light in ways that reveal the secrets of the universe. The near-infrared spectrograph, or NIRSpec, is one of the key instruments for exoplanet studies. It can split light into its component wavelengths, creating spectra that show which molecules are absorbing light at specific wavelengths. This is exactly what astronomers used to detect carbon dioxide in TRAPPIST-1E's atmosphere. The mid-infrared instrument, or MIRI, extends Webb's vision further into the infrared, allowing it to detect the thermal radiation emitted by planets themselves, not just the light they reflect or transmit from their host stars. Keeping these instruments cold is essential for their operation. Infrared detectors must be chilled to extremely low temperatures to prevent their own thermal emissions from overwhelming the faint signals they're designed to detect. To achieve this, Webb employs a massive 5-layer sunshield, roughly the size of a tennis court, that blocks heat and light from the sun, Earth, and Moon. This sunshield creates a temperature difference of hundreds of degrees between its sun-facing and space-facing sides, allowing the telescope and its instruments to remain cold enough to function optimally. The sunshield itself is an engineering masterpiece, made of layers of a material called captin. Each layer is thinner than a human hair but strong enough to withstand the stresses of deployment and the harsh environment of space. The layers are separated by gaps that allow heat to radiate away into space, creating a cascade of cooling that drops the temperature on the cold side to around minus 370 degrees Fahrenheit. For MIRI, which operates in the mid-infrared and requires even colder temperatures, a dedicated cryocooler brings it down to minus 447 degrees Fahrenheit, just a few degrees above absolute zero. All of this technology, all of this careful planning and engineering, comes together to enable observations like those of TRAPPIST-1E. When Webb observes a transiting exoplanet, it must capture data with exquisite timing and precision. The planet's transit across its star might last only a few hours, and the atmospheric signal represents an almost imperceptibly small change in the star's brightness. Webb must stare at the star before, during, and after the transit, collecting photons and feeding them into its spectrographs, all while maintaining absolute stability and pointing accuracy. The data that comes back from these observations isn't immediately revealing. It requires careful processing and analysis by teams of scientists who must account for systematic errors, instrumental artifacts, and the light from the star itself. They must subtract the star's spectrum to isolate the contribution from the planet's atmosphere, a process that demands sophisticated computer algorithms and deep knowledge of both the telescope's characteristics and the physics of stellar and planetary atmospheres. When the results finally emerge, they take the form of a spectrum, a graph showing how much light is absorbed or transmitted at different wavelengths. Certain dips or features in this spectrum correspond to specific molecules. For carbon dioxide, there are characteristic absorption features in the infrared that create a distinctive signature. When astronomers saw these features in the spectrum of TRAPPIST-1E, they knew they were seeing evidence of carbon dioxide molecules in the planet's atmosphere, absorbing starlight as it passed through. The statistical confidence required to claim a detection in exoplanet science is high. Scientists must be certain that the signal they're seeing isn't just noise or an instrumental artifact. They typically require a detection significance of several sigma, meaning the probability that the signal is due to random chance is extremely low. For the carbon dioxide detection on TRAPPIST-1e, the data met these stringent criteria, giving astronomers confidence that the signal is real. But one detection, however significant, is just the beginning. Science progresses through repeated observations, independent confirmations, and the accumulation of evidence from multiple sources and methods. Webb's observation of TRAPPIST-1e will be repeated, with longer exposure times and observations at different wavelengths to search for other atmospheric constituents. Other instruments on Webb, and eventually other telescopes, both in space and on the ground, will add their own data to the growing portrait of this distant world.